Okay, thank you very much for inviting me to give a talk to your conference. My title has changed slightly from the original submission for the reason that a week ago the organizing committee asked me if I could give a plenary lecture, so I expanded it a little bit. Hopefully it's a little bit more broad and interesting like that. Of course, I will talk for several things that several people have contributed, and I have put some of the main contributors here in my talk. And I should start explaining what is ECMWF. ECMWF is an independent intergovernmental organization which was established in 1975, and it is supported by 22 member and 12 cooperating states. ECMWF's purpose is to develop a capability for medium-range weather forecasting and to provide such forecasts to our member and cooperating states. It is a complementary service to the National Meteorological Services, and in fact, we work with them in research. We collaborate closely. Sorry about that. I'm just trying to. Okay, I did to close my thumbnail. We collaborate closely with our member states. We provide numerical weather prediction, but also supercomputing services. Some of our member states run their limited area models in our supercomputers, and we provide training. We are based in Reading, which is a picture here, although now I'm based in my home because of coronavirus restrictions. We work from home, most of us, well, the vast majority of us, except of the people who look after the operations, the shift, the operational model running. So ECMWF has a strategy for global weather predictions, and a main theme of our strategy is to provide detailed Earth system simulations of the past, present, and future for the prediction of extreme and high impact weather events up to few weeks ahead. And in order to achieve this, increasing the resolution of our model is very important. If we have a look what happens today, we run a global atmosphere ocean weather prediction system and different configurations of our global model. For example, we have a 10-day deterministic forecast which runs at 9 kilometers horizontal resolution, and that has 137 vertical levels. We run 15-day probabilistic forecast. That is a set of 51 separate 18-kilometer forecasts which use perturbed initial conditions in order to capture the uncertainty of the atmosphere. And these run at the lower vertical resolution of 91 levels, but we plan in a few months' time to increase it to 137 levels. We also run a monthly and seasonal forecast system, which consists of a 51-member and sample at 35 kilometers horizontal resolution. Additionally, we run a multitude of atmospheric composition global environmental forecast as part of the Copernicus Atmospheric Monitoring Service of the European Union. Global climate reanalysis, and in all these components, we plan to increase the resolution. So the current plan is that by 2022, we'll be running the ensemble prediction system between 9 and 11 kilometers. While we would like to move to a really high global resolution of approximately 4 kilometers for our ensemble system by 2025. And resolution will continue increasing. So before I move to more technical details, I'll just show a slide of how the equations that we use, the equation set that we use to forecast the weather looks like. It's the weather is an initial value boundary condition problem, and currently we're using a hydrostatic primitive equation set, which is given by these equations here on the left. We have the momentum equation. Here is a pressure gradient term. This is a geopotential term, which gives us the orographic effects, the Coriolis effects, and on the right-hand side we have forcing terms, which come from atmospheric physics, for example, friction, turbulence, convection, and many other physical effects. We have the temperature equation, moist tracers, Omega is the vertical velocity here. We have 7 Moist tracers and ozone. Here's the continuity, mass continuity equation and the hydrostatic equation. We also have a non-hydrostatic version available, but currently is not in operational use in ECMWF. However, as we share a dynamical core with other member states, they use the non-hydrostatic equation set and the non-hydrostatic numerics of the ECMWF model, which is called IFS. Now, the question is, how do we solve these equations? The technique we use is called the spectral semi-implicit semi-Lagrangian technique. IFS is a very accurate and efficient global weather prediction system. In fact, it produces, according to WMO metrics, the most accurate global weather prediction in the world currently. And the numerical methods do play a big role into achieving this. And so if we want to have a look, which are these key numerical methods that are used by the dynamical core, which is the set of prognostic equations, it's we have spectral transform discretization, which allows us to compute very accurately the horizontal gradients in our equations. It doesn't suffer from pole problems and allows us to use an efficient Helmholtz solver, which we can solve directly. And we also use it is also a constant coefficient, which means that we decompose the matrix coefficients at the beginning and then at every time step going into the back substitution. It also has a very efficient time stepping due to the semi-Lagrangian semi-implicit approach, which allows to use very long time steps, but with very low dispersion and phase errors. This is one great feature of the semi-Lagrangian semi-implicit method. Furthermore, our grid point calculations are efficient for the reason that we use a Gaussian grid, which works together with a spectral transform method, and we will see the details in the following slides. So that avoids the clustering of grid points near the pole, which avoids a singularity problem as the resolution is fairly uniform everywhere on the globe. In addition, we use domain decomposition with maximum wind halos, and this picture shows this maximum wind halo approach. So every MPI task has a halo region which is wide enough, and the width is determined by the wind, by a maximum assumed wind, and that allows us to communicate only through the halo without the need to send messages. Of course, it has the drawback of being expensive in memory. The equal regions decomposition approach is depicted by this picture here, and shows that these are MPI tasks covering the globe, and more or less they have the same region everywhere, the same number of points approximately, and there are plenty of points, about 9 billion points, if we consider all the prognostic variables and all the vertical levels and all the equations of our model. These are I mentioned about the great things of the semi-implicit, spectral semi-implicit semi-Lagrangian method. However, there are some drawbacks, of course. And one drawback these days is the high communication cost. So the spectral transform suffered from a high communication overhead and poor scalability as we increase further and further the resolution and reach 1 kilometer. Furthermore, as I mentioned, the halos are good because we don't have to pass messages around. However, as you increase a lot the resolution, you get poor memory scalability. The constant coefficient Helmholtz approach, although it is great and allows to solve the elliptic equation that we have to solve at every time step in our system, very efficiently and very fast, it does suffer from instabilities at regions of very steep slopes when the resolution becomes very high, for example, around near to 1 kilometer. And last but not least, the big hurdle of semi-Lagrangian advection scheme is the lack of formal conservation properties. Now, it's interesting to see the history of this method and how it has been so successful. The ECMWF model has been operating since 1979, but at the beginning, until 1991, it was a spectral semi-implicit Eulerian model, not semi-Lagrangian, on a full Gaussian grid. So that means that it was not reduced during the poles, and the resolution in terms of longitude was constant. So you have many, many points near the pole. But at that stage, there was a horizontal and vertical resolution upgrade in the plans, almost doubling this resolution. And this upgrade required approximately 12 times the available then CPU power. But funding was available only for 4 times the CPU, for only a 4 times CPU increase. Finally, the semi-Lagrangian method on a reduced Gaussian grid came to the rescue, and by being so much more efficient, not only it was possible to do this resolution upgrade, but it turned out that the model was faster than expected. It was 6 times faster than its predecessor. However, it's interesting to see what is the situation nowadays. This is an intercomparison of the ECMWF model IFS against the leading American models that took place 5 years ago on a dynamics only case. At 3 kilometers, the dry baroclinic instability, which includes 10 traces. It's an idealized setup, and we're interested only to see the efficiency of the dynamical core. That's why we use that test in collaboration with American colleagues. What we see here, that if we look at time to solution on the left plot, the IFS is the fastest of all models. However, as we increase the number of cores and we push it to higher and higher number of cores, we see that the IFS is the least scalable, which means that eventually, although now it is the fastest, eventually, as time goes by and we increase the resolution, we won't be able to run it on our supercomputers without doing any further work. So we have a development strategy which has 2 main threads. We would like to exploit both algorithmic and hardware improvements to extend the life of our current spectral, semi-implicit, semi-Lagrangian dynamical core. And this can be done by to a large extent by code refactoring to run seamlessly on different exascale platforms. And that is either massively parallel CPUs or CPUs with GPU accelerations or other technologies such as FPGAs. And the other thread, the other main effort is to keep improving core algorithms of our dynamical core in terms of efficiency and accuracy, so that we can we will be able in the coming years to run high resolution efficiently on modern architectures. At the same time, we develop an alternative non-hydrostatic finite volume dynamical core, which we believe will be advantageous at very high resolutions, as it addresses conservation issues with the current method, steep slope stability issues, and scalability issues. But we think that the time for this dynamical core will be when the resolution goes below 4 or 3 kilometers. And now, if we take a quick look how the spectral transform semi-implicit semi-Lagrangian solver looks, here is a schematic diagram which shows 2 things. Some calculations taking place in grid point space, and some calculations take place in spectral space. So we calculate horizontal gradients, and we do the semi-implicit solver in spectral space as well as the horizontal diffusion, while some other computations such as the semi-Lagrangian advection, the physics of the model, and the product of nonlinear terms are calculated in grid point space. And of course, we need the method to move from grid points to spectral coefficients. And this is done by fast Fourier transforms. So we calculate first the Fourier coefficients, and then through a Legendre transform, which is Gaussian quadrature, we go to spectral space. Then with an inverse Legendre transform, we get back the Fourier coefficients, and then with inverse fast Fourier transform, we can get the representation of our fields in grid point space, and we can produce sensible meteorological output. For the vertical, we use hybrid pressure vertical coordinate and a finite element discretization, which is based on cubic spline elements. This allows us to do very accurate vertical integrations with noticeable positive impact in the stratosphere, and it gives us accurate vertical velocities, which leads to accurate vertical transport. And this is described by this paper by Unz and Ortal in the quarterly Journal of the Royal Meteorological Society 2004. Now, a few things about the spectral transform. Well, it's a series of expansion methods, and every field is represented as a series of the base functions is spherical harmonics, which is basically the product of this exponential term with the associated Legendre polynomials. Phi is the latitude, lambda is the longitude. In reality, we don't use all these infinite terms. In practice, we use truncated series. And the particular form of truncation we use is called triangular truncations, because this N and M indices lie within this triangle and provide uniform resolution of the entire surface of the sphere. A key component for the efficiency of our model is the grid we use. The spectral transform, as I mentioned earlier, we need a grid, and we need to we move from spectral coefficients to grid point representation, and for that we need a grid. And the grid we use is the octahedral Gaussian, reduced Gaussian grid. Here we do the semi-Lagrangian advection and our physics parameterizations. It's called octahedral because the projection of an octahedron onto the sphere. This is our octahedron here, which surrounds the sphere, and it's very simple to construct this grid. We start from the pole, and every row below, latitude line below, we add one more point. So 1, 2, 3, 4, and so on. We ignore the first 4 points, and then we start from here. We go all the way down the equator. This grid replaced the previous reduced Gaussian grids, which is called the linear grid, and gave us improved effective resolution, improved mass conservation, and efficiency and scalability, as we can see by this plot, which shows that we can achieve at the same grid point resolution more forecast days per day with our new grid. And if you're interested to find out more, you can read these references in ECMWF newsletter. Furthermore, we are doing, there's a big effort currently at ECMWF to provide a version of our model that can seamlessly run either on CPUs or GPUs. We use source-to-source translator tools to achieve this. And here what I show is results from running the spectral transform package on Summit, which used to be from Oak Ridge National Laboratory, which would be the fastest supercomputer on the world until recently. And we can see here that with the GPUs, the blue line, it is possible to achieve the operational performance required, which is indicated by this line in terms of time to solution for the spectral transforms. Once we increase the number of GPUs beyond a certain level, and that is not achievable with CPUs. So we think that having the capability to run our model on GPU system will help us a lot towards implementing our strategy for high resolution. And currently, there's a lot of work done on physics, to port physics on GPUs. And for the advection, we're not sure if we're going to execute on GPU and CPU in the future, but if we like to do that on GPUs, it is likely to use another version of the semi-Lagrangian advection scheme, which has been implemented in a software library developed in-house by Willem de Koning called Atlas, and provides flexible data structures and grid mesh generation capabilities and operators for numerical weather prediction and climate modeling. And Atlas is a system that underpins all our efforts for future developments, including the development of the new Dynamical core FVM. It is open source, and it has a C++ or Fortran interface and supports various grids, structure or unstructures, allows parallel mesh generation, and mesh-to-mesh interpolation, mathematical operators, and many things. Another thing we have recently done, and we expect to become operational in a few months, is we have produced a single precision version of our forecast model. And here we see a comparison. The single precision version is about 40% faster. And this is our current 9 kilometer resolution model. How many forecast days it achieves per day. With single precision, we see it achieves almost twice as many. This is in double precision. And what is important is that as we increase the resolution, it seems that even in the current computer, it is possible to run within 1 hour, which is our critical time window for operations, our 5 kilometers, there is a resolution on our model at 5 kilometers. Of course, if we want to go higher resolutions, we have to do more work, which as I mentioned, we are working hard on that topic now. Now, how is our solver, semi-implicit semi-Lagrangian solver works? Well, a key concept is the concept of backward trajectories. In order to find the solution, we need to compute backwards a trajectory. We take every grid point at every level of the globe, and for every grid point, we work out where an air parcel, which is sitting there now, was at one time step before. And this is the departure point. Once we find these departure points, then it is possible to find the solution by interpolating the field we have now at the departure point. It is a Lagrangian thinking. And if we consider a prognostic, this general form of a prognostic equations, with psi is a prognostic variable and f gives us the right-hand side, D is the Lagrangian derivative, and V is the wind, the horizontal wind components, and the vertical velocity, which is in eta terrain foreline coordinates. If we expand the right-hand side in linear and non-linear terms, the linear terms are either existing in the equations or they're non-linear terms that are linearized. Then we can write the discrete form of these equations in this equation here. It's a Crank-Nicolson essentially, but in Lagrangian form, Lagrangian thinking, we see that when we are at time t, which is the current time that we know the solution, we're at the departure point, but when we are at the future time, we're at the grid point. So we need to compute the departure points, and once we compute the departure points, we interpolate them. As for these terms, although they are in future and they're not known, they can be extrapolated because they are slowly changing. These terms can be found are linearly implicit and can be solved by a linear system through means of a linear system. Now, in order to do this, to compute the departure points and to perform this extrapolation, we use a scheme called settles, which comes from a Taylor expansion around the departure point, which is shown here. And it assumes an approximation, which I have indicated here. And from this equation, we can come to this. And this is an iterative scheme, which we can solve by performing separate iterations. We start some initial condition from some initial value, and then we iterate, and then after a few iterations it converges, and it gives us the departure point. From that we can find, here is in Cartesian framework, but from those we can find the longitude and the latitude, and then we have to do the same for the vertical coordinate. So this is how, in a few words, we find the departure point. Once we find the departure point, then we have to extrapolate these terms, and then we have to interpolate to the departure point. And at the end, these different variables are eliminated in terms of a single elliptic equation, the Helmholtz equations that we solve, and we find the solution to divergence, and through back substitution, all the remaining variables. Now, the problem with this extrapolation, which I mentioned earlier, is that it can generate noise. And this shows in this plot here, if we have some noise time series, which can happen in the stratosphere, for example, you can have vertical velocities that are very close to zero, up and down. Now, if you extrapolate them, you begin to see error growth. If you have smooth data, no problem, it works fine. And because of this this noise can generate poor temperature forecast in regions of the stratosphere. So the solution was simple to detect these time extrapolations and switch off using to a first order time scheme. And that's what we did a few years ago and improved greatly the ERA 5 reanalysis. As we can see here, there were these big jumps. This is difference from an instrument, satellite instrument. So the analysis was disagreeing with the observations, and that problem was solved by implementing this hybrid scheme, which switches to first order time scheme when this phenomenon of noise occurs. And we can see the practical impact here in the stratospheric warming forecast. Here we have the original version of the model, which didn't have this fix, is unable to produce this stratospheric warming. Well, with this modification, it agrees well with the observations, the analysis in this case, which is relies on observations to be produced. And it is possible to do this forecast 7 days in ahead, which is important because the stratospheric warmings can give us useful information for coming cold spells. Now, another issue with the semi-Lagrangian scheme is that although it converges, although it's conditionally stable, it has some restrictions. The departure points, in order to converge, they have to satisfy a Lipschitz condition. So the distance of two successive iterations in our departure point algorithm should be smaller than the previous one multiplied by Lipschitz constant. So if this Lipschitz constant is smaller than 1, then it converges, or if it's greater than 1, it doesn't converge. And that depends on the time step. So when we use very big time step, it is possible to generate a sequence which doesn't converge. And we found that this happened in practice a few years ago as we increased the resolution of our model, although we used shorter time step because we had steeper velocity gradients that generated a larger deformational Courant number or Lipschitz number. And analyzing the forecast results, we deduced that we need either to increase the number of iterations or to decrease the time step. Oh, sorry. So here I show you what happened in practice. We have the we take the difference between the departure points of the second iteration minus the first iteration, and then we perform one iteration. We see that this difference, this distance shrinks, but 3 iterations are not enough. And if we do another one, it shrinks further, but we have to do one more in order to bring it even down. This is the region of a tropical cyclone. Now, if we had if we have the time step, in this case, convergence, it's much fast. But if we have the time step, then we have a much more expensive, we have to allow twice as much time for our simulation, which is unaffordable. And here is the impact on tropical cyclones. With original setup, we had 3 iterations. We could see some negative potential vorticity in the stratosphere, which shouldn't be happening, increase the number of iterations, and the solution agrees with the solution with half the time step. And in addition, we get a nice reduction in geopotential height error over the Himalaya region. And I will skip this. There are other ways to do the iterations through a dynamic control, or we can use accelerate the convergence by use of better predictor. Perhaps it's more interesting to say a few things about the option. As you know, as I mentioned, in ECMWF, we use an ensemble prediction system, and we are interested in quantifying uncertainty. So the question is, can we quantify uncertainty in our solution of transport equations? The answer, we have started experimenting with this. And what we have recently done is to introduce a stochastic term in our departure points. For example, if you consider the advection of a scalar, the solution is given by this simple expression, it's a hyperbolic PDE. Now, if we add the stochastic term in our departure point, then we can come with this equivalent expression, which means that this is equivalent to adding a stochastic term at the right-hand side. And that can help us to quantify the uncertainties in areas where the dynamics can experience errors, for example, in areas like a tropical cyclone or near jets. This stochastic term depends on the difference between two successive iterations, and this work was inspired by what I mentioned earlier with the analysis I did the departure points, and is currently implemented by my colleague Sarah Jane Locke, who has got some very nice results, and which shows that when you introduce this stochastic flow-dependent term in the advection scheme, then you can increase the spread and you can increase the skill of the ensemble here. With blue lines means that we have increased the skill of the ensemble. With these red triangles, it means that we have increased the spread. So that's something that is recently started, and is a promising avenue, especially as we increase further the resolution to quantify the uncertainty of our transport equations. Another big issue with the semi-Lagrangian scheme is the mass conservation. The problem is that semi-Lagrangian advection cannot conserve mass, and we have interpolation errors which result into conservation errors. The mass conservation error depends very much on the nature of the transported variable. For example, for the total atmospheric mass, it is quite small, and that shows here, the red line. It is less than 10⁻³ for a 10-day forecast of the initial mass, 10⁻³ of the initial mass of the atmosphere. However, if you consider some traces that are localized in nature and have sharp gradients, it can get quite large. As we can see here, is 0.2% for a 20-day forecast of a tracer, which is, in this case, is CO2, but only confined in the boundary layer. Or here is confined only in the stratosphere, and here is the entire CO2 field everywhere, which is well mixed with the atmosphere, and in this case, it doesn't have large gradients and produces a small mass conservation error. Conservation is particularly important for long-lived carbon tracers and for climate simulations. It's not a problem for numerical weather prediction at this stage. And one thing that is worth mentioning is that monotone interpolation limiters we use in the advection scheme increase the mass conservation errors further. And also one avenue to improve the conservation is through more accurate numerics. Because a very accurate scheme, even if it is not designed to conserve, should conserve better than a less accurate one, because it will simply satisfy the continuity equation for the tracer at greater precision. And we can see this here for ozone, for example. Let's take the red line, it's easier, which shows the total mass of ozone as it evolves in 20 days of forecast when we use a trilinear interpolation scheme to the departure point for ozone. Now, if we switch to a tricubic, the mass conservation error, the red line, reduces by a factor of 8 approximately. And then if we use a bicubic in the horizontal but quintic in the vertical, it is reduced by another factor of 2. And the same for the other traces, which are confined, again, are copies of the ozone field, idealized experiments confined at different regions of the atmosphere. We see this big jump, the reduction in conservation error as we move to cubic and then to cubic and quintic combination. Of course, if your tracer is very localized and has sharp gradients, the low order may be more suitable. But even if your conservation error is small, such as the case with the CO2, it is important to eliminate it completely, because you run long simulations and it's a long-lived gas and you want it to have good conservation. And for that, we use the mass fixer approach. We have various approaches. One is a simple proportional mass fixer, which corrects every grid point by the ratio of the mass after advection and before. But 3 years ago, we developed this scheme called, which is based on the Bermejo-Conde approach, which is uses a locally weighted method in order to correct at every grid point the mass, while it restores the global mass of the tracer. It is a Lagrange multiplier approach, and it ensures that the global norm of the difference between the corrected field and the original field is minimized subject to the constraint of that the global mass remains constant. And it has and this weight factor here depends on the interpolation error. So it is a bit like correcting the interpolation error at every grid point. And we can see that it works better than this proportional scheme. If we compare it here, we have the simple proportional fixer and the Bermejo-Conte. We see there is much more detail here in this correction. This is at 16 kilometers, this is at 8 kilometers resolution, and we see much more correction in areas we have emissions and in the northern hemisphere, where is most of the CO2. And even more important, if we compare against observations, this is our various CO2 observation stations, and we take our results for 16 kilometers and 8 kilometer resolution. We see that we have an error. This is without any fixer. We use the proportional mass fixer. It corrects the error, the mass conservation error, but it leaves unmodified the concentration error. But with a Bermejo fixer, not only we correct the mass conservation error, it corrects the transport error as well, and it comes closer to the zero line here, as we can see, both for high and low resolution. And finally,
Michail, it's in just 3 minutes.
Yes, I'm finishing. It's my last two slides. Thank you very much. And finally, we have been recently experimenting with another scheme, which is called COMAD. And if you're interested in the details, I won't have time to explain, or you can look at this paper, which is a cell average departure point scheme, and it computes a correction factor to the interpolation weights that depends on the convergence of the wind. And with this COMAD, it's possible to reduce the amount that the mass fixer corrects even further, especially if we don't use a monotone limiter, but we substitute it with a positive definite limiter. It is possible to reduce the correction that the fixer inserts by a factor of 6. There is some other work currently done by my colleagues. For example, there is an effort to reduce stratospheric temperature biases, and this has been achieved partly with the introduction of the quintic in the vertical interpolation scheme, which I mentioned earlier. There is work in investigating high-order integrators for departure point schemes. We investigate multiple grid approaches for chemistry and to improve parallel communication algorithms. And finally, we would like to develop a high-order PAW discontinuous Galerkin semi-Lagrangian scheme, which is compact stencil method and multi-tracer efficient and will allow long time step capability, which has huge potential for communication savings and accurate solution of transport equations. And basically, that's all I had to say. I have some concluding remarks here for you to read if you want. So I hope